All right, let's dive right in. We're about to explore one of the biggest and, frankly, weirdest questions in all of science. What is reality? Really? Richard Feynman, one of the sharpest minds in physics, he famously said that this one single experiment, it holds the entire mystery of the quantum world. And as we're about to find out, wow, he was not kidding. So, to really get a grip on the strange nature of what's real, we have to start right here. Think of this experiment as, well, the scene of a crime against common sense. Okay, so the setup itself is super straightforward. Just picture a gun that fires single electrons, one after another, at a wall that has two little vertical slits in it. And behind that wall, there's a detector screen that just makes a mark wherever an electron hits. Sounds simple, right? But this super simple setup, it leads us to our first major clue in this whole mystery. So what should we actually expect to see on that screen? If we're just using our everyday logic. Well, logically, you'd think these electrons would act like tiny little bullets, right? Each one has to go through either the left slit or the right slit, and they just pile up behind those two openings, creating two simple, clean bands on the screen. But that is not what happens. Not even close. Instead of two nice, neat bands, we get this. It's an interference pattern with lots of light and dark stripes. This is exactly what you'd get if each electron was a wave that passed through both slits at the same time and then interfered with itself. And this is the evidence that just makes your brain hurt. I mean, even when we fire them one at a time, so they can't possibly be bumping into each other, they still slowly build up this wave pattern. It's like each electron, all by itself, is somehow exploring both paths at once. So this brings us to this absolutely crucial idea, wave-particle duality. A quantum object, like an electron, isn't just a particle, and it isn't just a wave. It's something that can act like either one, and it all depends on what kind of experiment you're doing. So let's take this investigation to the next level. What happens if we try to cheat? What if we try to actually catch the electron in the act of going through both slits? As detectives on this case, our next logical step is pretty obvious. Let's put a tiny little detector, a spy, right there at the slits. We're going to finally see once and for all which slit each electron really goes through. And boom, this is the smoking gun. The very instant we start watching to see which slit the electron goes through, it completely stops acting like a wave. The interference pattern just boop, vanishes. And what are we left with? Just two bands, exactly what common sense told us we should have gotten in the first place. This incredibly bizarre thing is called the observer effect. See, in our normal world, looking at something doesn't change it. But in the quantum world, measurement isn't just a passive look. The very act of measuring, of observing, fundamentally changes the outcome. Which leads to this absolutely mind-bending question. A question that gets right to the heart of quantum mechanics and has physicists arguing to this day. Is the universe fundamentally different when we're not looking at it? So, how on earth do you explain something like this? Well, for the better part of a century, two major interpretations have been battling it out, each one trying to solve this profound mystery of what reality even is. So let's meet our two main suspects in the lineup. Each one gives us a completely different picture of what the universe is actually like, under the hood. Okay, so let's break down the key differences here. On one side, you have the Copenhagen view, which basically says reality is just this fuzzy cloud of probabilities until we look. It's not definite. But on the other side, Bohmian mechanics says, no, reality is always definite. It's always real. We just can't help but disturb the crime scene when we try to look at it. Now, the Copenhagen interpretation, this became the standard, the orthodox view for decades. It basically says that before we measure it, the electron literally does not have a definite path. It exists only as a wave of possibilities, and our active measurement is what forces that wave to collapse and choose a single spot to be. The reason this became so popular is that it worked. The math made incredibly accurate predictions, even if it meant we had to throw our common sense picture of the world out the window. The philosophy was basically shut up and calculate. But Bohmian mechanics offers this really compelling, though less common, alternative. It says, no, the electron is always a particle. It always has a real, definite path. No fuzziness. So how does it make a wave pattern? Well, it's being guided by a hidden physical wave, a pilot wave. A great way to think about it is like a tiny surfer on a huge ocean wave that we can't see. The surfer's path is totally real, but it's being dictated by this invisible wave. And our clumsy measurements, they inevitably disturb that pilot wave, which in turn changes the surfer's path. That's why the pattern disappears when we look. It lets us keep our sense of a real world, but we have to accept there are these hidden parts we can't directly observe. So, where does all this leave us in our big detective story? I mean, which one of these completely different views of reality is actually the right one? The incredible truth is, we still don't know for sure. And that's not some failure of science. That is the frontier. This is the point where our most basic, fundamental, common sense ideas about how the world is supposed to work just completely fall apart. And that leaves us with the ultimate question from this entire mystery. It's a thought that gets to the very core of existence itself. What is the world really like when we're not watching?